Hi everyone, welcome to all of you on my YouTube channel. I am Ankit Mishra. So I'm going to start with the revision series of chemical reactions in part 2. So I'll start with the non-ideal reactor. So first, here you can see the real, practice in real practice, no reactor is ideal CSTR. So they actually deviates from ideality. So let's say you have CSTR. So in the CSTR, you will see the characterizing variable will be same throughout the reactor. Let's say CHCB, all of these characterizing parameters, let's say concentration, temperature, and pressure will be same throughout the reactor. So there is no special variations of any parameters in the CSTR. Then that is called as ideal CSTR. And again, if there is no axial mixing in plug flow reactor, then that is called as ideal PFR. Right. So here you can see that in for the ideal CSTR, characterizing variable are uniform at any point inside the reactor, and for ideal PFR there is no axial mixing and radial mixing will be infinite. So what sorts of the region that involves a reactor becomes a non-ideal reactor? So here you can see if I'm talking about the CSTR, so there will be dead zone, right? So in dead zone, what will happen, some molecules will get entrapped over here and it will spend very a long time inside the reactor, and due to this particular region, what will happen, the concentration in this particular dead zone will get different from the concentration in another part of the reactor where this characterizing variable are well mixed. Is that clear? So this kind of characteristics makes a ideal CSTR and non-ideal CSTR, and after that bypassing also. So let's say some molecules will enter and directly without getting completely mixed inside the CSTR, it will complete it will directly get bypassed from the reactor. So this also makes the no creates the non-ideality of the CSTR. And again, circulation. So sometimes what will happen, some molecules will be continuously circulating inside the CSTR due to this rotor, and it will create in the vicinity of the this rotor, and this creates the circulation. So all of these kind of problem creates non-ideality in the CSTR. So due to this particular region, you can see that if I'm going to track the molecules, the residence time for all of these molecules should be different, right? So if residence time of all these molecules are different, then this creates the non-ideality in the CSTR. Now coming to the non-ideality in the PFR, so again dead zone is there. So you can see in PFR also some molecules will get entrapped in this particular zone, and it spends the residence time of this particular molecules will be more than the expected. So it creates the residence time distribution. And if there is an axial dispersion, so in an ideal CST PFR, you will see there is no axial dispersion, but in non-ideal PFR you will see there is a axial dispersion. And again channeling also. So sometimes you will see that due to the channeling, let's say if we have three different molecules, and due to this particular channeling, you will see the residence time of all these molecules will be different. So this creates a non-ideality. See, so in order to understand these non-ideality in the PFR and CSTR, so RED experiment, that is our residence time distribution experiments, have been performed earlier, and that gives you the a distribution of the residence time of all these molecules inside the reactor. So in order to understand these things, you'll see here that a tracer is being injected inside the reactor, and the concentration of tracer at the exit of the reactor has been you know observed, and based on this, the concentration versus time plot has been plotted. And here you can see that there is a distribution of concentration with respect to the time, and you can see that this looks like a bell-shaped curve, something like that. So we'll see how these things are working. So now when it comes to the how many types of tracer inputs experiments are there, so there are importantly two kind of tracer input experiments are there: pulse tracer input and experiment, and a step tracer input experiment. So when I'm talking about the pulse tracer input experiments, here you will see that the concentration of tracer is injected in the form of pulse, and at the exit concentration of tracer has been you know observed, and you can see this kind of distribution is there. So and again in a step tracer input experiments, you will see at t equals to 0, a maximum concentration, let's say Cmax of tracer concentration, has been injected inside the reactor, and it will continue like that as a step function. And at the exit of the reactor, the concentration versus time plot of the tracer has been observed, and it goes like that. So if I'm talking about the area under the concentration versus time curve, so CT versus DT curve, so if C out versus C, so here you can see that the number of molecules per unit volume means concentration of tracer at N naught is number of moles of tracer, and V naught is volumetric flow rate. So N naught by V naught will be equals to 0 to infinity and CT dt, right? So N naught by V naught, you can see that 0 to infinity CT dt, where CT dt is the area under the curve of concentration versus time. Now coming to the exit rate distribution function, ET is called as the exit rate distribution function, and ET/DT is the fraction of tracer molecule at the exit of the reactor between time t and t plus dt. So at different time interval, you can see that ET/DT will be equals to moles of the tracer at the exit of the reactor between time t plus dt divided by total number of tracer feed at the reactor, that is N naught. Okay, so if I am going to observe the concentration of tracer at the exit of the reactor versus time, so I'll take a differential element, that is delta t, and I want to observe how many number of moles of tracer was between time t plus dt, or concentration of tracer at the exit of the reactor between time t plus dt, right? So you'll see at time t1, t2, t3, I'll observe the concentration c1 and c2, and after that what will happen, I'll divide the concentration C1 divided by whole area, right? Because you will be knowing the area of this curve, and you'll divide this thing. So finally you will get ET, exit rate distribution function, and that exit rate distribution function is the CT divided by 0 to infinity CT dt, something like that. So you can see that 0 to infinity CT dt will be the area under the concentration versus time curve of the tracer at the exit of the reactor. Okay. Okay, great. So after that, I'll move towards the next thing, that here also you can see that at particular time t1, we will calculate concentration, t2 concentration is c2, and at different time interval, you can calculate the concentration of the tracer at the exit, and you can plot the concentration versus time curve. And after that, you can calculate the area of concentration versus time curve, and again the whole area will get divided by every concentration, that at t equals to t1, c1, c was c1, and all of these things. And from here you can get the ET versus time curve. So you can very easily calculate the concentration versus time curve into ET versus time curve when you are dividing the CT divided by the whole area of concentration versus time curve, right? So this is very simple thing, and based on this, lots of numericals came on the gate also, and this year also there is high probability that they can ask the question. But now coming to the ET versus time curve area, so that used to be equals to 1, 0 to infinity, ET dt equals to 1. And obviously it is very natural thing that because you are calculating the CT versus area under the curve, so ultimately you'll add all of these things. So in above numerator and denominator, the thing will get things will be same, and definitely it will be going to cancel out with each other, and it will be equals to 1. So area under ET versus DT curve will be equals to 1 between 0 to infinity integral limit, right? Now when we talk about the FT, that is the fraction of molecules at time t1. So if I want to calculate how much molecules at the exit of the reactor between time 0 to t1, or between time t1 to t2, or at up to any particular time, that is called as the cumulative age distribution. Means 0 to time t1 we can calculate, right? So if I am calculating ET versus time curve, and at time t1, if I am calculating how much molecules were there, or what was the concentration of the molecules at the exit of the reactor between time 0 to t1, you can calculate the area 0 to t1 ET dt, and again you can calculate area between 0 to t2 ET dt, right? So this will give you the the fraction of molecules between time 0 to t1 and 0 to t2. And if you want to calculate the fraction of molecules at the exit of the reactor between time t1 to t2, you can calculate t1 to t2 ETDT, or you can subtract 0 to T2 ETDT minus 0 to T1 ETDT, and that will give you the fraction of molecules at the exit of the reactor between time T1 and T2. Is that clear? So it will be there. So FT is called as the cumulative age distribution function, and the formula for FT is equals to 0 to T ETDT. Okay. Now coming to ET versus time curve, here you can see if I am calculating FT, means fraction of molecules between time 0 to T1, that is 0 to T1 ETDT, and a fraction of molecules between time 0 to T2, that is 0 to T2 ETDT. So if I want to calculate the fraction of molecules that has spent time in between T1 to T2 inside the reactor, that is T1 to T2 and FTDT, right? So you can calculate these things like that. So FT is defined as 0 to T ETDT, and if I differentiate dft by dt, you will get this thing. So if you have, let's say, FT versus time curve, and at every time you can calculate the slope of FT versus time curve, and again if you plot the slope at every point, you will get the value of ET, right? So ET is equals to CT by 0 to infinity CT dt, and FT is equals to 0 to T ET dt, or DFT by dt equals to ET. That is very very important parameter. You should understand this instead, and the formula, based on the formula, mostly questions have been asked. Okay, so that is very very important thing. Now moving towards the next part, that since every fluid element spend different interval of time inside the reactor, hence in order to find average of all the time, we have to calculate the mean residence time, right? So here you can see that how we can calculate the mean residence time, because all of these molecules that is coming at the exit of the reactor here will be spending different interval of time or different time, let's say t1, t2, t3. So what I'll do, that in order to calculate the mean residence time, we'll go to 0 to infinity T et dt divided by 0 to infinity et dt. So 0 to infinity et dt will be equals to 1. Why? Because area and the et versus time curve will be equals to 1. Okay. And from here you can get the formula for T mean residence time. T bar is equals to 0 to infinity T into et dt. Is that clear? So you have, let's say, plot of T et versus time, and if you are able to calculate the area versus T et versus d, so it will give you the mean residence time. And now coming to the variance. So variance, it measures the spreadness of the curve, right? So how much deviations are there from means to another value, a specific value. So sigma square is called as the variance, and it has been defined as 0 to infinity T minus T bar whole square et dt. So let's say if this one is sigma 1 square, this is sigma 2 square, and this one is sigma 3 square. So in sigma 1 square, you can see that spread is very less compared to second and compared to third. So here you can see the spreadness in first was very less compared to third. So you can see the variance in third was much greater than variance in second. So again, another formula of variance can be written as 0 to infinity T square et dt minus T bar whole square, where T bar is the mean residence time, and that can be calculated as 0 to infinity and T et dt, right? So all of these things are there, and again standard deviations can be calculated as root over variance, right? That is sigma. Now coming to the step tracer experiment in step tracer experiment. So obviously, whenever we are injecting a tracer, so we can apply the tracer valence inside the reactor. So let's say we notice the volumetric flow rate, and here you can see that tracer is being injected inside the reactor, and the tracer concentration is, let's say, Cn, right? So if you apply the tracer valence, in minus out plus generation minus consumption equals to accumulation, because there is no generation and consumption, because we are not considering any chemical reaction that is happening here, and accumulation is 0 because obviously this is a flow reactor. So whatever the thing that will be coming, that will be going out. So I'm assuming that this is working at a steady state condition. So here you can see for the tracer experiments, V naught into C naught into Ft plus V naught C naught into 1 minus Ft is equals to V naught C naught. So here you can calculate Ft is equals to Ct divided by C naught. What is Ft? Ft is the cumulative age distribution function, and Ct is the concentration of tracer at the exit of the reactor at time t, and C naught is the initial concentration, right? So from here you can see for the tracer step tracer input, Ft is equals to Ct divided by C max. Is that clear? And what is Ct divided by Cmax? So Cmax, you know that this one is the Cmax, that concentration you can know, and at any particular time the concentration you can calculate, and after that you can plot the Ft versus time curve, that is Ct by T naught, C naught. Okay. So let's say if this one is concentration versus time curve, and for concentration versus time curve, you are supposed to calculate the EP curve, FT curve, and T bar and sigma square. So obviously FT is equals to CT divided by C naught. So C naught is how much? That is CT by C max. So CT, you know that, and C max is 20. So you can calculate the ET, FT, and obviously T bar is equals to T ET dt, and sigma square is equals to T square ET dt minus T bar whole square. So this formula already I have discussed, and you can calculate this thing. Now coming to the RTD in ideal CSTR. So if I'm injecting any pulse tracer input inside the CSTR when delta T is tending to 0 and the tracer input is C input, right? So for the pulse tracer, it has been injected for a very small interval of time when delta T tending to 0. So negligible concentration of tracer is assumed. So rate of tracer input minus rate of tracer output, that is equals to rate of accumulation of tracer, right? So let's say accumulation is there inside the reactor. So if rate of input, because we are assuming a pulse tracer experiment is there, so rate of tracer input is 0 and rate of tracer output is Ct into V naught, that is equals to d by dt of V into Ct. So once you do this mathematical calculation, this is just a ordinary differential equation, and once you substitute, so for pulse tracer input experiments, you will be getting Ct equals to C naught e to the power minus T by tau. When you have concentration function, now you can calculate Et is equals to Ct divided by 0 to infinity Ct dt, right? And after that also Ft can be written as Ct divided by C max, or you can calculate 0 to T Et dt. So from here, once you will calculate these things, you will be getting the formula of Et and Ft, and the formula is like Ct equals to C naught e to the power minus T by tau, Ft is equals to Et equals to 1 by tau e to the power minus T by tau, and Ft equals to 1 minus e to the power minus T by tau. So this is very important formula. So this is formula is only valid for pulse tracer input in CSTR. Okay. So again, based on this formula, you can plot the curve, and also you can calculate lots of numericals. And when you calculate the T bar, that is mean residence time, that is equals to 0 to infinity T into Et dt. So you have the formula of Et, and once you calculate these things, you will be getting mean residence time of the tracer inside the reactor is equals to tau, that is the space time. So for the mean residence time, used to be equals to the space time for the pulse tracer experiment in the continuous state reactor. Okay, so now coming to the next part, that is also very important, pulse tracer input in the plug flow reactor. So here you can see that for plug flow reactor, again I am telling you that we are injecting a tracer for very small interval of time, delta t equals to 0, and we notice the volumetric flow rate having concentration of the tracer is C input, and you see that whenever a tracer is being injected into the plug flow reactor, it has to travel this particular length, right? The length of the reactor, and at this particular time it will come. So means the molecules are going to spend tau p interval of time, and the tracer that is being injected at t equals to 0 here inside the at the inlet of the reactor, after tau p time you will see the same concentration. So if I want to calculate the what is the outlet concentration of tracer at the exit of the reactor, that is C input into t minus tau p. Is that clear? So where tau p is the space time for the plug flow reactor, right? So C input is, let's say, C naught delta t, like a direct delta function, because we are injecting a pulse tracer input, right? So pulse tracer input can be very well defined in terms of direct delta function. Is that clear? Okay, great. So here you can see that C output is equals to C naught and del t minus tau p. So when I'm talking about the properties of direct delta function, that is very important. So minus infinity to infinity, del t minus a dt will be equals to 1, means the area under the direct delta function generally used to be equals to 1 when base of the uh, at x-axis, that will be the thickness will be tending to 0, and at y-axis it will go to infinity. So that why, so that's why we'll see area under the direct delta function will be equals to 1. Okay, now second function that is also very important when I am integrating direct delta function, that minus infinity to infinity ft and del t minus a dt. So here you can see inside the direct delta function that t minus a is there, and if a lies between minus infinity to infinity, then the integral value of minus infinity to infinity ft and del t minus a dt will be equals to fa. So where ft will be given to you, and at t equals to a you will substitute, you will get the answer. So let's say here, if you from here this particular problem, if you'll see minus infinity to infinity 3t square into del t minus 2, that is equals to, so here you can see that 2 will lie between minus infinity to infinity and ft is 3t square. So directly now you can substitute t equals to 2 here in this function, and you will get that is 12. So again you can calculate that 3t square into del t minus 1. So 1 will lie between minus 4 to 1, so 4 minus 4 to 4. So again you can directly calculate this thing. But again, if you will see in this particular problem, minus 4 to 4, 3t square into direct delta function t minus 10. So 10 is not going to lie between minus 4 to 4. So here you can see that the functional value will be 0, right? So this is the property of direct delta function. So the time interval at which these things is happening, so it should be lie in between the integral limit. So if it is not lying inside the in between the integral limit, then definitely the value will be 0. Okay, so here again another problem, that minus 4 to 4 t minus 2 whole square del t minus 2. So here you can see in the function 2 lies between minus 4 to 4, so then definitely the functional value will be equals to t minus 2 whole square, so where you will have to substitute t equals to 2. So ultimately here you are getting 0 due to the functional value, right? So here you can see that Ct equals to C naught del T minus tau p. So tau p is the space time for the plug flow reactor. So now when we talk about the ET, exit distribution function, that is Ct divided by 0 to infinity and Ct dt. Okay, so that will be equals to C naught del T minus tau p divided by 0 to infinity G naught del T minus tau p. So here I have told you that tau p will lie between 0 to infinity. So the area under this curve will be equals to 1, right? So C naught is a constant, it will take it will come outside, and C naught will get cancelled out. So finally the exit edge distribution function you will be getting et equals to del t minus tau p. Okay, and when we have got the et value, then very easily we can calculate the value of ft, and the value of ft can be defined as 0 to infinity and ft dt. So 0 to infinity del t minus tau p dt, and that will be equals to 1. So the exit edge distribution, sorry, cumulative edge distribution function for pulse tracer input in plug flow reactor will be equals to 1. So ct we know, that's del t minus tau p, et that is del t minus tau p, and ft equals to 1. And when we talk about the mean residence time, that is the formula for mean residence time used to be equals to 0 to infinity et into et dt. So 0 to infinity t and del t minus tau p dt. Okay, so now this one is the function, and tau p will lie between 0 to t, so directly it will be equals to tau. So tau p, so from here also you can see that for the pulse tracer input, the tau equals to tau p equals to t bar, means mean residence time for the plug flow reactor reactor will be equals to the space time. And when we calculate the sigma square, that will be equals to tau p, means tau p square. Okay, so this looks like C input and this looks like C output, but after a particular time, that is t equals to tau p, you will be getting C output, and having the function will be equals to the initial function, right? Now coming to the step tracer input experiment, that is very very important. So in a step tracer input experiment, you are injecting a tracer inside the continuous state tank reactor, let's say, and the concentration of tracer is, let's say, C naught, and at t equals to 0 you have injected, right, and the concentration is continuously constant, right? Continuously it is in link. So when we talk about this thing, so again you can apply the tracer valence in C star, that V naught into C naught, that is concentration of tracer at the input, in minus V naught into CT, that is out, that is equals to accumulation, that is d divided by dt of volume into CT. This is just an ordinary differential equation. So when you will solve this thing, that you will get CT equals to concentration of tracer at any particular time equals to C naught into 1 minus e to the minus t by tau, right? So where tau is the space time for the reactor, right? So this is very easy thing. Now once you have calculated CT, so you can calculate the value of ET, that is equals to CT divided by 0 to infinity, and obviously CT dt, that is area under the curve of concentration versus time. So the value of ET you will be getting 1 upon tau and e to the power minus t by tau. Is that clear? And now from here you can calculate the value of FT also, that is equals to 0 to t into ET and dt. So you have calculated dt. So the value of Ft from here you can see that 1 minus e to the minus t by tau. Okay, so you have calculated the value of Ct, Et and Ft. So this one is the pulse step tracer experiments results for continuous state tank reactor, that is Ct, Ft and Et. Okay, now again you can calculate these things for the plug flow reactor also, that is not very much important. But now coming to the, when we are connecting RTD, when we do the experiment, RTD experiments for CSTR PFR in series, you can see that concentration curve CT will be equals to C naught into e to the power minus t minus tau p divided by tau m when t is greater than tau p, and that will be equals to 0 when t is less than tau p. So because at till t equals to tau p, you won't be able to get any concentration, because this molecule has to travel inside the PFR also. So once it will come out of the PFR only, then you'll see the any signal for the concentration of the tracer, right? And this is valid for when we are connecting CSTR in PFR in series, or first PFR and then CSTR in series. So concentration formula for both of these is same. And when I am talking about the exit rate distribution, that is equals to 1 upon tau. From here you can see 1 upon tau and e to the power minus t minus tau p divided by tau m when t is greater than tau p, and that will be equals to 0 when t is less than tau p, right? So from here you can calculate the exit rate distribution function, and this formula is only valid for both of these, when CSTR is connected in PFR and when PFR is connected in CSTR. Is that clear? Now, so in this case, you can see that conversion X is a function of only RTD. I mean, because if you are connecting CSTR in series with PFR, and PFR in connected in series with CSTR, so only valid, this formula is only valid when the reaction is a first order reaction, and this is not valid for reaction any another than another order having, let's say, for second order reaction, third order reaction, that is not valid. So here you can see that the conversion inside the reactor is one function of RTD, as well as the kinetics, and as well as the types of the reactor. Okay, so types of the reactor. So this model is only valid for the first order reaction. So when I'm talking about RTD alone is not sufficient to determine the performance of the conversion for the same parameter. Another parameter is also required, right? So the mixing of the reacting fluid element is one of the most important, controlling factor that affects the conversion of reactant inside the reactor. So RTD is not sufficient to determine the performance of the reactor. So RTD plus kinetic and mixing, all of these three things becomes very important, and all of these three things come together, and then only you can calculate the conversion or what's happening inside the reactor ideally. or accurately. So in order to understand these things, that how these kind of things are working and how you can club all of these parameter together, so then we study the zero parameter model and one parameter model. So in zero parameter model, generally we study complete segregation model and maximum mixedness model, and in one parameter generally we study Rankine series model and axial dispersion model. So first I'll start with the complete segregation model. So in complete segregation model, you can see that the overall conversion, that is average conversion inside the reactor, that will be equals to 0 to t and xt et dt. This is a zero parameter model. So here if you know the exit distribution function, that is RTD function, then very well, very easily you can calculate the overall conversion inside the reactor by using this zero parameter model. And xt you can calculate for first order, zero order, second order, and any another order reaction. So something like that. So here you can see that xt. So for first order reaction, let's say xt will be equals to 1 minus gram minus kt for the constant volume reaction system. And for CSTR, for pulse tracer input, you can say that's et equals to 1 by tau gram minus t by tau. So you have xt, you have et, and once you will put this thing in this formula for the complete segregation model, and you will be able to calculate the overall conversion from this particular reactor, right? But again, you can very easily do these things for the second order reactor or any other of reactor also. And again, this is valid for the plug flow reactor also. So in plug flow reactor, already I have told you that the pulse tracer input, the excitation function will be equals to del t minus tau p, and xt is 1 minus pi minus kt. So when you put these things over here, so this is the function and this is tau p. So directly you will get 1 minus pi minus k tau p. So here from here you can calculate the average concentration of plug flow reactor while using the complete segregation model, that is a zero parameter model. Now coming to the one parameter model, in which I'll be talking about the tangent series model. So here you can see that a tracer is being injected inside the first reactor if an CSTR is connected in series having volume of all CSTR is V, and the volumetric flow rate at the inlet of the reactor is V naught. So you can see that space time I am assuming here is tau 1 equals to tau 2 equals to tau 3 equals to tau n. That is the space time, that is V divided by V naught. V is the volume of the individual reactor. So x bar equals to 1 minus Cn by C naught, where Cn is the concentration of the reactant molecule or CT at different time interval. And here you can see that x bar can be written as 1 minus Cn divided by C naught. So for first order reaction, you can see that CT equals to for first reactor, you can say that C1 equals to C naught into minus T by tau, and even you can calculate very easily. So from here, you can directly calculate what is the concentration that is coming from the nth order reactor, that is CNT, and that is C naught into T by tau whole to the power n minus 1 into 1 upon n minus 1 factorial into minus T by tau. But Gate is not going to ask the formula or any question on this particular formula. So if they are giving you any formula, then you can very easily do the balancing or mass balance of all of these components inside the reactor, and you can calculate for any kind of order, any order reaction. But if for nth order, they are not going to, I mean, Gate is not going to give you any question. But once you know the value of ET, you can calculate the FT and anything. But this graph is very, very important. So you can see when reactor is only one, then the formula for the pulse tracer input like et equals to 1 by tau minus t by tau, it will follow like that. But when you increasing the number of tank in series, then what will happen, it is going to follow like that. So the variance of mean residence time is decreasing, and ultimately it will reach to it will follow like direct delta function, that is the plug flow reactor, right? So if you are increasing n, then the reactor, if you are increasing n number of CSTR in series, and tending to very, very large, then it will follow the plug flow reactor profile. So again, you can calculate the variance, that is 0 to infinity t square et dt minus t bar whole square. And from here you can also calculate the number of tank that is required to get this kind of distribution, that is n equals to sigma square divided by t bar whole square. Sigma square, that is t square et dt minus t bar square, and t bar is the mean residence time. So sigma square equals to n equals to sigma square divided by t bar whole square. So this formula is very, very important, very frequently get used to ask question on this formula. So definitely whenever you are going for the Gate examination, you should remember this formula. And from here you can see that you can calculate these things, mean residence time and variance from this particular curve. And once you calculate calculate these things, then definitely you will be able to calculate the number of tank in that number of tank that was connected in series, right? So from here, this formula you can see n equals to sigma square by t bar. And this question has been asked in GATE 2024. So again, this kind of questions become very, very important. Now coming to the axial dispersion model. So axial dispersion model is valid for the flux flow reactor, and tank in series model is valid for the continuous tank reactor. And tank in series model and axial dispersion model both follow the one parameter model. So generally in ideal plug flow reactor, you will see that there is no axial mixing, but in real case scenario, you will see there is a convection and diffusion both is happening, and due to this particular region, what happens? The axial dispersion will be there. So if I apply the tracer balance in a small thickness element dz, and here you can see at z equals to 0 fz, and so two different kind of flux will be there: molar flux and the diffusive flux, convective flux and diffusive flux will be there. So Na is, let's say, your convective diffusive flux, and FZ is a convective flux. So if I'll apply both of these flux balance here, so at Z equals to 0, NAZ and FZ is there, and at Z plus delta Z, FZ plus delta Z, and NAZ plus delta Z will be there. So if I talk about the flow of flow due to the dispersive flow, so you can write Na bar equals to Na into cross sectional area, that is DAB into dCA by dZ, and AC is the cross sectional area. So FA can be written as CA into U and XA. So when we do the balancing, FA at Z plus NA at Z plus Z minus FA at Z plus delta Z plus NA at Z plus delta Z into cross sectional area, that is D by dt of tracer balance, dNA by dt. So NA can be written as concentration into volume, and volume can be written as cross sectional area into the thickness. So cross sectional area will get cancelled out. So finally you will get FA at Z plus NA at Z minus FA at Z plus dZ minus NA at Z plus dZ, that is equals to d by dt of C into dZ. So once you do this mathematical expression, you will get dFA by dZ minus d by dZ of NA equals to dC by dt. Okay, so FA can be written as CA into U, and NA can be written as d diffusivity of the tracer or any molecules, and dCA by dZ. So once you do this expression, finally you will get a partial differential equation of the second order in at an steady state condition. Del C by del T is equals to d del 2 C by del x square minus U del C by del x, or del C by del Z if I'm assuming the axial coordinate is Z direction, right? So at a steady state condition, del C by del T will be equals to 0, and you can see that d del 2 C by del x square minus U del C by del Z is equals to 0, and finally you will get this kind of equation, right? And when you non-dimensionalize this formula, like T star, C star can be written as C by C naught, where C naught is the initial concentration at Z equals to 0, and Z star will be equals to Z by L. So this will lie in between 0 to 1 limit, and T can be written as T by U, L by U, where L is the length of the reactor and U is the average velocity of the tracer molecules. And when we substitute all of these equations in this particular formula, that del C by del T equals to d del 2 C by del x square minus del C U del C by del Z. And once you do this calculation, finally you will be getting a non-dimensionless number, or the dimensionless number, that is d by U into L, that is called as the dispersion number. And this indicates that the transport of the tracer due to the dispersive flow divided by transport of the tracer due to the convective or bulk flow, right? So this this particular dimensionless number, that is called as the dispersion number, tells you the relative importance of the transport of the tracer due to the dispersive flow compared to the transport of the tracer due to the bulk flow or convective flow. So if let's say d equals to 0, means transport of the flux tracer due to the dispersive flow will be 0. There is no axial dispersion, and that shows the dispersion number will be 0. And if dispersion number is 0, that then this indicates that there is no any axial motion or axial transport due to axial dispersive flow is 0. Then this is the case of plug flow reactor, ideal plug flow reactor. And when d equals to infinity, means transport due to the bulk flow will be equals to 0, means transport is happening only due to the dispersive flow, and this scenario is only valid for the continuous state tank reactor. So okay, so these kind of questions can be asked in your examination. So and 1 upon dispersion number is called as the Packley number. So Packley number can be defined as UL by D. So when Packley number is 0, then that is the case of your ideal C star, and when Packley number becomes infinity, then this will be the case of your ideal PFR. Okay, so with that I'd like to I stop this lecture here only. So this was the revision class for the non-ideal reactor, and this is very, very important. In the next class I'll be talking about the heterogeneous catalytic reactants. Okay, thank you. See you in the next lecture for the catalysis.